So far, we've been talking about solutions in a pretty conceptual way, so that we have all the information we need to write out reactions for some basic solution chemistry. Soon, we're going to dive back into the quantitative side of things, taking those reactions and doing calculations with them. But before we can start doing reaction stoichiometry again, we need to define some new units and discuss some new skills relating to handling solutions. If you're doing bench chemistry with solutions instead of dry reagents, then chances are you're going to be mixing different volumes of dissolved compounds together in order to get a reaction started. In order to know how much of a dissolved compound you're delivering in those volumes, you have to know the concentration of your compound in solution. That is, how much of your compound is dissolved in a given volume. The most common unit in chemistry for concentration is called molarity, and it's a derived unit that's composed like this. The number of moles of a compound that's dissolved per 1 liter of solution is the molar concentration. This derived quality is going to be the case for all the concentration units, and you never want to forget that these two ways of writing the concentration units are equivalent. The capital M abbreviation is a useful shorthand, but the moles per liter notation is what will actually help you with unit conversions. Molarity isn't the only way to specify concentration, though, and other units are sometimes used depending on the context. Molality is moles of solute over kilograms of solvent. Mole fraction is moles of solute over the combined total number of moles. And mass percentage is the same thing, except with mass units instead of moles. Parts per million are also sometimes used for very low trace amounts of dissolved material, and they have equivalent definitions involving volume or mass in the denominator depending on whether you're working with an aqueous solution specifically or something else. These are the definitions, and you might need to do some quick conversion problems in this unit to familiarize yourself with the different concentration units. Hopefully, though, we can recognize the general pattern. With all these units, we're relating the amount of material that we specifically care about in the numerator to the bulk solution in the denominator. Before you can do reactions with solutions, you often have to make them up to a desired concentration in the lab. You usually define a target volume for the solution and a target concentration, values that you choose based on whatever you need it for, and then you just calculate the number of moles of a compound that need to be in that final volume. This type of approach is reflected in the example problem here, and it's our first look at using concentration units in dimensional analysis. Just like usual, we start with the simplest quantity in the problem, which describes what we have to work with, or in this case what we want to have at the end of the preparation, and that's the desired volume here. The next step is to recognize that the desired concentration in molar here can be rewritten directly in terms of moles per liter. And hopefully from there we can see how this could be used. Concentration is basically a conversion factor between moles and volume of solution, so we can perform the appropriate unit conversions now to get an answer in terms of moles. Now, back at the lab bench, there is actually one more consideration. I was careful to say that our chosen volume represents the final solution volume here, not the volume of solvent added when preparing the solution. This is an important distinction because if you started with your target volume of solvent and just dumped in our calculated moles of solute here, the added solute will actually change our final volume slightly. So we don't want to do it that way. Instead, the best practice is to add some solvent to your prep vessel, less than what you're eventually going to need, and then dissolve your solute, and finally bring the final volume up to the desired level with some additional solvent. One more thing about solution prep that's really important for everyday lab work. What if you were asked to make up a certain amount of solution at a certain concentration, but instead of starting with dry reagents, you already have a stock solution prepared that's at a known concentration? This is a common situation, especially in biochemistry, where materials are often made up and put into short-term storage as aqueous stocks. Well, in this problem, you might imagine the general procedure. The stock concentration here is higher than the concentration of the solution we need to make, so all we have to do is take a certain amount of the stock and put it in a new container, and then add some more water until we have the right final volume and the right final concentration. There's a few things here. First, there's just the general principle that we're applying with this logic. If you start with something at high concentration, adding more solvent is going to lower the concentration. We have a special name for this sort of procedure. We call it dilution, and in math terms, we'd say that volume and concentration are inversely proportional to each other. You also may have noticed that the key thing to figure out here is how much of the stock to put in our new flask before we add the extra volume. If you watch the ideal gas law video in this series, you might already see how we can figure this out. We want to know how much of the stock to start with so that we can end up with a specified final volume and concentration. Because concentration and volume are inversely related, We can set up an equation that directly relates the initial and final conditions here that looks like this. C1V1 equals C2V2. This is the dilution equation, and we can just plug in and solve. At this point, we have some basic knowledge and skills relating to handling solutions and the concentration units that define them. You'll want to be sure that you're comfortable with these concepts before examining reactions in a quantitative way. Thanks for watching.